Okay, so let's discuss something. And we haven't met in a very long time, so maybe let's do a little bit of review. And perhaps our entire discussion will be the review, but with some minor adjustments. You know? I'm gonna be we're gonna have a review, I'm gonna be very incremental. Every time I'll tell you the same thing, but like with one minor detail added. Okay. Right. So what were we talking about before? We were talking about tight binding models, right? And we'll continue talking about tight binding models. Actually, I should always have. I realized that if I put chalk on here, then I don't use it. But then if I have it in my hand, then I use it. So I always need to have chalk in my hand. Okay, so tight binding models. Do you agree? So let's quickly recall what this was about. So I had, first of all, one of the first assumptions was that the Hilbert space was some set of states, alpha sub m, right? Where m is the, so this is the state that corresponds to the electron at the alpha type of atom in the mth unit cell of the lattice. Do you agree? Right? So I'd have some lattice of atoms, right? This lattice would have some unit cell that's periodically repeated. Do you agree? These unit cell I can index by integers. Do you agree? And alpha is the type of atom. Okay? 2, we assume that the Hamiltonian is, first of all, is commutes with translation by some lattice vector, right? So T m dot A acts on alpha n by sending it to alpha n plus m. Okay, so the translation operator takes something in the nth unit cell and moves it to the n plus mth unit cell.
What's going on left over there?
Here?
T, M, A, and then what?
So this is H. H commutes with the translation by m dot A. M are integers, A are reciprocal lattice vectors. So this is just translation by m1, a1, m2, a2, m3, a3. That gives me a vector.
Yeah, I was more confused about the thing you just erased.
This is what I erased.
Yeah.
So this is the translation operator that translates my state by this vector.
Yeah,
Okay.
with regard to being on the left of the thing that's not erased.
It was the fact that it was written there was not important.
Okay.
This is one sentence.
Yes.
Okay. And this is just what the translation operator is. Okay. Sorry. Also, when I mean m dot A, this is like bad notation. It's not a dot product. I mean this is some element of z, whatever my lattice is, zn. So this is say a few integers, however, whatever dimension my lattice is. And then this are my lattice vectors, a1, a2, a3. So this is m1, a1 plus m2, a2 plus m3, a3. Okay, I'm just too lazy to write this. Right? Oh, sorry, does not have the hat, A has the hat, sorry. A has the vector set. Do you agree? Okay, if I was in 2 dimensions, there would be 2 vectors. If I was in 1 dimension, there would be 1 vector. Okay. It's okay. Yeah. Good. Right? And then 3 was, okay, H commutes with this, and we also say that H is written in terms of these hoppings. So H is written as, can be written as N, M, alpha, beta, whoops, like this. So, or in other words, sorry, this is the sum over N, M over alpha over beta. Okay, and in other words, perhaps how we wrote it more often in second quantized notation, this was alpha dagger N beta M. Okay, where this is an annihilation operator for the beta type of atom, this is a creation operator for the alpha type of atom. And I sum over types of atoms and the hoppings. Usually there's like a minus or whatever. Okay, does this make sense? Do you see how this kind of Hamiltonian, why it would be called a hopping Hamiltonian?
Was I here for this one?
Probably. We talked about this like last semester and then this semester. So just look at this Hamiltonian. Why does this look like a hopping Hamiltonian? What is hopping from where to where? Suppose I was on the beta
You're
mth.
on beta and then you hop to the
Yeah, if I was on the beta mth state and I applied the Hamiltonian, then it would pick out the beta mth state and send me over to the alpha nth state with some hopping amplitude. Okay, that's why it's called the hopping Hamiltonian. Okay, right? And so this was the setup. How did we solve this? Okay, well, to solve this, right, we did a kind of Fourier transform. We defined alpha k to be the sum over all unit cells of e to the this has plus. Yeah, this has plus. K dot m dot a. This is like this. Alpha m. Okay, and actually we defined 2 kinds of bases. They're practically the same. I should really draw some pictures, but plus tau alpha, where tau alpha is the position of atom in unit cell. So maybe I should draw an example. Yes.
I think there should be a 1 over square root n.
Ah, that's right. That's right. But the 1 over square root n is like, it's important, but it's not important, but it's important. Okay. That's very right. Okay. Let me just draw a picture of the setup, because I'm writing like a bunch of stuff in indices, and unless you've already thought about this for a very long time, and I don't think it's entirely good. So suppose I had a hexagonal lattice. Let me try and draw a hexagonal lattice. There should be getting pretty good at this one now. And suppose on this hexagonal lattice, I have two distinct sites. I have A and B sites. I have this, 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 this. Oh, whoops. Oh, sorry, this is incorrectly drawn. These are distinct, distinct, distinct. Good, 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 good. This and this. And then I have the B sites. Do you agree? So these would be the A sites, and these would be the B sites. Do you agree? And okay, I'll give you a moment to finish copying. And what you can realize is that, wait a second, this is a lattice that I can build out of just two atoms. If I take any two A and B sites, say take this one and this one, do you agree? Then the rest of the lattice I can build by translating this pair of atoms in different ways. Okay? So in this case, I guess one choice of lattice vectors would be like this and like this. So I don't know, A1 and A2. Maybe I'd want this one to be A1 and then this one to be A2. Doesn't matter. Okay? Do you agree? And then I'd be writing, I'd choose one unit cell to be kind of the 0, 0 unit cell, and then every other unit cell I'd describe in terms of kind of moving from the 0th unit cell by some number of lattice vectors. Do you agree? Yes? Okay. Then, what by, what's it called? By, what was the theorem? By block theorem. By block theorem, we knew that H can be restricted to the span of alpha k for fixed k. Okay? So, in other words, I can write down my Hamiltonian. So I'm gonna, say I'm gonna do this for graphing. I can write down my Hamiltonian like this. I can write down my Hamiltonian as some matrix which only acts on kind of the K subspace for a given momentum state. Okay. And so what is the basis of this matrix? Basis. So look, H restricts on the span for fixed K. So what other thing can I iterate over? There's two letters.
Yeah.
What's the other one?
Alpha.
And what did it mean physically?
Type of atom.
The type of atom in the lattice, right? So for every type of atom in my distinct type of atom in my lattice, by distinct I mean one that I cannot translate. Like two atoms are distinct if I can't translate from one into another while also keeping the Hamiltonian invariant. But anyway, point is, for every type of atom, I have some like Fourier transform momentum space vector, momentum state degree. For every type of atom, I can look at this kind of linear combination, right? This is for some fixed alpha degree. And so this is, going to be the state A, K, and this is going to be the state BK. For this graphene example. So this is for graphene. This is how the thing would look like, roughly. Okay. And now if I want to find the eigenvalues, right, so the energies, I just need to diagonalize this 2 by 2 matrix if I have 2 different types of atoms. If I have n different types of atoms in my unit cell, then I just need to diagonalize an n by n matrix for every momentum. Do you agree? So this is what we got a while ago. And why is this useful? Because, well, before it was, this complicated thing where I could hop from here to here to here to here, whatever it was. And that was very complicated. But now I just need to, for every momentum, diagonalize like a 2 by 2 or an n by n matrix, and that's very easy, relatively speaking. Okay. Do you agree? Then we said that I can plot the eigenvalues of this matrix. So I think this matrix, actually, these are the twiddle ones. I want to do the twiddle ones. Okay. So this matrix is often called H of K, right? It's kind of the kth the contribution to the Hamiltonian form of momentum K. Do you agree? Right. So I can kind of decompose H to be a sum of H of K's, or a sum over K. Okay. So I can plot the eigenvalues of H of K as a function of K. Do you agree? Okay. And I get some kind of plot. Whatever they are. Okay, whatever the bands might be. And so this is energy, this is K. So I'm drawing this in a kind of one-dimensional thing. If you had a two-dimensional system, your momentum would be two-dimensional. So you would plot this as like a surface over, 2 dimensions. Do you agree? But also you can choose a particular path in your surface that would be of interest. Do you agree? Okay. This part makes sense how we got from here to here.
Wouldn't be continuous though, right?
Usually it would. If your matrix is some function that depends on K usually continuously. Do you agree? And the eigenvalues are a continuous. The eigenvalue the entries of this matrix depend continuously on K, and so the eigenvalues are the solution to some polynomial equation.
Yeah.
And so surely that should depend more or less continuously.
I get that. What does it mean for non-integer K? Because I thought K corresponds to K through this all lattice.
No, sorry. There was alpha m where m, this is different.
Mm-hmm.
So alpha m, this is talking about mth point in the lattice. When I write K here now, I now mean this linear sum.
Oh.
This is no longer this. This is a different notation. This is like a Fourier transform, kind of this.
Okay.
Or another way, one way we motivated of getting these states, this is this is an eigenstate of the translation operator.
Okay.
So if you apply T onto this one, T sub m, which shift everything by m, whatever, m dot a vector, then this will just, I'll get the same state in a periodic system. I'll get the same state with like a extra phase, which will be the eigenvalue.
Okay.
And so we realize that if H commutes with this T, and these are eigenvectors of this T, do you agree? Then if I rewrite H in terms of this basis, right, H should restrict on the eigensubspace of T. So it would be advantageous for me to rewrite H in terms of this basis. And this is what I did here.
Okay.
I just rewrote the Hamiltonian in this new basis.
Okay. And
When I write K, I mean momentum, so a Fourier transform like this. When I write M, I mean in real space, this is the electron is on this atom.
okay, so we're summing across momentum eigenstates.
This, where? Where do I sum across momentum eigenstates?
So like, what is K indexed by?
K is some, like if our lattice is n-dimensional, K is some n-dimensional vector. If I'm in 2 dimensions, my momentum is 2-dimensional. If I'm 1 dimension, my momentum is 1-dimensional.
But do you have an indexing set?
Good point. If my system is periodic, I think K, well, it depends. You can think of K as a continuous variable, if you wanted to. It's defined in some region of your plane. Well, on a torus, but okay, whatever. I want to go back that far. Okay, but K is some vector. Okay. Good. And I can plot the energies as eigenvalues as functions of K. Okay. And we realized one thing I could do is, I could fill these bands. Or what do I mean? If I have 2 bands like this, right? This means that for every possible momentum, I have 2 available eigenstates of my Hamiltonian that I could fill. Do you agree? I can put an electron to have a state here or a state here. So suppose we fill bottom band. So you know that, maybe the K's should really be what? They should be indexed by integer times pi over L. Do you agree? Remember, like if you put something in a box, then only the allowed frequencies are n pi over L, right? So if my K are allowed n pi over L, then I have some discrete amount, like finite discrete amount of states that I have available. Do you agree? And then I can kind of fill all the states available in the bottom band. And then I'll keep the states available in the top band empty. So I'll put only so many electrons. Okay? And you can imagine that at 0 temperature, this is what will happen. I'll only fill the lowest energy eigenstates. So there is electrons in these states. Do you agree? But then there are no electrons in these top states. And now I realize that suppose I wanted to add an electron, or I wanted to move an electron around, it's very hard to do that if the bands look like this. So if bands look like this. So if bands, what time is it? Okay, we have 10. If bands are gapped, do you agree? If the bands are gapped, like they are here, right? There's some finite gap at every point in time, some energy gap. Do you agree? Between the lowest and the top band. If bands are gapped, you see it's hard to move electrons due to Pauli exclusion. Do you agree? So this is kind of a heuristic explanation. This is kind of whatever. But suppose you wanted your electron to change into a different state. Do you agree? So take any electron, say this one, right? It's in this state. I want it to go to a different state. Well, what are the states that are available? It's only the ones in this top band, right? There's like a finite amount of energy that I need to spend to do that. So it's kind of hard to change it. There isn't something that's kind of close to it that I could change it into. So it's hard for the electrons to change states. And so you get what's called a band insulator. Well, because I think you didn't come to the time where I talked about this. Because I already talked about this. We're still reviewing. Yes. So you get what's called a band insulator. So if I have bands that have a gap, then I have a band insulator. Well, none of this includes interactions. So maybe with interactions something else would happen. But at a single particle level, this gives me some insulator because the electrons, in some sense, can't change state, so they can't quite move around. Yeah, once again, this is like a momentum space picture, so maybe it doesn't quite make sense to say what does it mean for electrons to move around, because this is momentum space, not real space. But okay, we can think about it in this way, in this simple way. Do you agree? Okay. Good. And so we want to kind of study these band insulators. Okay. So what I really want to do is maybe, what I want to do is try and okay, yes. Right. So now what we're going to do is we're going to try and use, so goal for the rest of the next, 20, maybe 25 minutes. The new goal is come up with some scheme in which I can classify band insulators and try and see why this might be useful for describing a finite system. So use topology to classify band insulators. Okay? Do you agree? Okay. So this is what we want to try. Okay. So, and first thing, I want to make the following comment. I think I've made this comment before, but now I'm going to kind of expand on this comment. Is that I want to, this whole block theorem stuff, right? Like this whole picture that we drew up, it only describes my system. It only describes a periodic system. Do you agree? The fact that I can do this implies that I have some periodic boundary condition, because otherwise it's not going to be an eigenstate of translation operator, right? If I had some finite lattice, and I truly had a finite lattice, and I translated every state, then it will translate off the lattice, right? So the Hamiltonian, that wouldn't make sense, and the Hamiltonian wouldn't be invariant under this. So this whole picture with Bloch's theorem is only for when I impose periodic boundary conditions. Do you agree? At the end of the day, so maybe this is not quite what I want to do. I want to use topology to classify band insulators and connect to finite systems. And connect this to finite systems. I think we're really, I think what we're going to do today is really more figure out how this relates to finite systems first, and then classifying, we don't have time. But okay, so we want to, right, this whole thing tells me something about periodic system, right? But I want to see, does this tell me anything about the finite system, right? Because at the end of the day, in the experiment, I have a finite system. And you would expect that maybe inside, if you were to look deep inside of my material, right? I have like a 2D material, suppose it's like really large, or at least its size is much larger than the spacing between the atoms, right? So then if I looked somewhere like in the middle of the material, if I was to stand there and look around, everything looks kind of periodic to me, right? Because the edges are so far away. And so maybe deep inside the material, this stuff would work. Do you agree? But maybe on the edges, right, where the assumptions of block theory fail, the assumptions of periodicity fail on the edges, there I would have, something interesting happen. Do you agree? And I want to figure out, what properties can I maybe infer, from the block theorem case about the finite system. Do you agree? Are the two in any way related? There's actually some kind of topological relation. So, actually, let me open this briefly. Yeah. Okay. Mm-hmm. Mm-hmm. Okay. So what I'm going to do is I'm going to look at the set of, I'm going to look at the set of finite Hamiltonians and find a way to relate them to like periodic ones. Okay? And I mean, that's pretty straightforward. So suppose I have my set. This has all the finite Hamiltonians. Finite type binding Hamiltonians. Okay. And then down here, I'm going to have my periodic ones. And so suppose here I have a point. It's going to be some Hamiltonian, which looks kind of like this. Do you agree? But I don't impose a periodicity condition. Meaning what? So how do you go from a finite to a periodic Hamiltonian? Okay. I'll explain it kind of on an example, and then hopefully the general case will be clear. So suppose I had some finite system of atoms. Do you agree? Okay, I have a system of 4 atoms. Do you agree? And then in the finite case, my Hamiltonian was that I can hop from this one to this one to this one, and like this. Okay, all with the same strength. Do you agree? Suppose this was the finite system. Okay. Then to make it into a periodic system, all I need to do is just add a coupling from here to here and from here to here. Do you agree? Like I've added a periodic boundary condition so I can kind of hop from this edge to this edge. Right? I made it periodic. Do you agree? And so this process, I'm going to call this the map pi. Do you agree? I kind of take a finite Hamiltonian and project it down to a periodic Hamiltonian. Okay? But here I also, yeah. Okay. Does that make sense? Yes. Do you agree? So pi is a map from finite Hamiltonians into periodic Hamiltonians, which pi imposes imposes periodic boundary conditions. So adds hoppings between edges in a periodic way. Edges in periodic way. Do you agree? Okay, that's what it does. It takes the finite Hamiltonian and then like adds hoppings to kind of the other edge to make it periodic. Do you agree? So first thing, right? And it's the way it does it, it adds these hoppings in a way that respects the hoppings in the bulk. So, there's a pattern of how the hoppings happen in the bulk. Do you agree? So suppose I had, suppose I had something where, say, the yellow atoms could like hop to their nearest neighbors. Do you agree? But then the orange atoms could only hop to like the red atoms and didn't hop to the yellow atoms for whatever reason, right? Like, suppose they only did. The orange atom would hop to the nearest red neighbor. Do you agree? Then, when I do the periodic boundary condition, this orange atom will hop to the nearest, to like this red atom. Okay? Does that make sense? So it's respecting whatever pattern you had going on in the bulk. Okay? Do you agree? Do these pictures make sense of like how you go from a finite to a periodic map? Okay, good. So we have this map. So properties of this map. So clearly this map is surjective. Do you agree? Okay, for now that's the only property we care about, and then we'll look at another thing now. So small comment. Clearly pi is surjective. Right, because for any periodic Hamiltonian, I can just take the periodic Hamiltonian and remove the boundary terms, like the boundary hoppings. Do you agree? I can take a periodic Hamiltonian and like cut it off. Do you agree? So there is some kind of inverse map, but this inverse map is not unique. So, there is a way to go back from periodic to finite, but not unique, because I can add like I can add like a constant potential on the edges, which would kind of get destroyed if I do this procedure. So I didn't explain that, but that's okay. But not unique. Okay. Can add finite energy on boundaries. Arbitrarily. So what I'm trying to say, and this is, I didn't specify it here, but suppose I had like a periodic system that goes from here to here. Do you agree? I can, to make it finite and not periodic, I can remove these two hoppings. Do you agree? But then I can also, like on this site, I can add like a C dagger C with some like on-site energy if I wanted to. And that would also be a perfectly valid finite Hamiltonian, or minus whatever. So I can like just add an arbitrary energy cost to be on the boundary, and okay, I'm allowed to do that. And that doesn't. Why am I allowed to do this? I'm allowed to do this because this doesn't break the periodicity in the bulk. I only care about like making sure that the bulk is periodic, but whatever is on the edges, whenever I go back with this projection, I will like force the edges to be periodic. So I'll like, if there's a term here, I'll like just remove it. If there's a term on the edges that's different from the bulk, I'll just remove it and make the edges like the bulk. That's what this procedure is supposed to do, right? But then if I go back from periodic to back to finite, right? Then I can like add something on the boundaries arbitrarily, and the periodicity in the bulk is the same. Does that kind of make sense? Okay. So like I kind of have a way to go from here to here, but not a unique way to go from here to here. Like if I wanted to, I could come up with something that, maps, but okay, that's good. And now I want to find, so we have some way now to connect, finite system to block system. Do you agree? This is finite, this is periodic. Do you agree? So I can go from a finite system to a periodic one, but what I really want to do, I want to find a way to kind of go from a periodic one to a finite one in some sense. And clearly we can't do it like in terms of the Hamiltonians. Do you agree? So we have to see maybe we can group the Hamiltonians somehow, so that perhaps there's a group here which corresponds to a group of Hamiltonians here in some one-to-one way. Do you agree? I want I want to find a one-to-one map between Hamiltonians here to here, but clearly there isn't a one-to-one map. So maybe I can group Hamiltonians based on some common property, right? And then I can group Hamiltonians here based on some common property. I can group Hamiltonians here based on some common property, right? And then maybe these groups will correspond in a one-to-one way. Do you agree? And that's where the topology is going to come in. All right. So I'm going to erase this. Maybe I'll redraw it here. Good. So now I'm going to define, so what I said before, I want to group things. Mathematically, if I want to group things, this means I want to define a what? No. No. We did this in 240. This was the first couple weeks of 240. But you looked at a specific example of this kind of thing on the integers. You looked at integers mod n, or mod p, whatever, mod p. And you realized that this integers mod p was, what was this mod p thing? It was some kind of, it lets you group integers, right? Yeah. Into equivalence classes. Okay? So what we want to do is we want to define an
equivalence class.
Close equivalence relation, and then get equivalence classes. So this is the goal. I want to define an equivalence relation. So say this Hamiltonian is equivalent to this one if a certain condition is met. Then I can break up each space into equivalence classes, and hopefully those equivalence classes will be one-to-one. Do you agree? And hopefully those equivalence classes will also mean something physical, but we don't have time for this. We're still in review mode almost. I think everything so far I've kind of said before, but now I'm kind of writing it out more explicitly. So first, let's define an equivalence class for the periodic Hamiltonians, okay? So define equivalence relation, I'm going to do it P, so among periodic Hamiltonians. So the equivalence relation goes like this. H is equivalent to some other H prime, and these are periodic Hamiltonians. Okay? If there exists a smooth gap preserving homotopy between H and H prime. Okay. So I wrote down a statement, and you should ask me a question about the statement. I'm assuming yes.
What's homotopy mean?
Great question. That's exactly the question. So, homotopy, colloquially, means I can kind of deform one thing into another continuously. Okay? So, this kind of shape is going to be homotopic to this kind of shape because, you can see I can continuously deform this shape into this shape. What does this? How can we write this down mathematically? So this is kind of annoying because usually when you write down a homotopy, you denote it with H, with capital H, and we already have a number, like everything is H. So maybe I'll call it F. So what does this mean? I.e., there exists a function f of t into the space of kind of linear operators on our Hilbert space. Do you agree? Such that f of 0 is my initial is one Hamiltonian, and f of 1 is the second Hamiltonian, and f is smooth in some sense. Do you agree? But I want more. I want the gap to be preserved. Do you agree? What did I mean by gap? I meant that, this is finite tight binding Hamiltonians, periodic Hamiltonians with a gap. So meaning that there's some spacing between the energies at all momenta. Okay? And so, we're gonna f is smooth, and for all t, f of t is gapped. Okay? So f takes in a, sorry. This should be from the unit integral, from 0 to 1 to the, sorry if you have to rewrite stuff. So it takes in some parameter, and as a function of this parameter, it takes this Hamiltonian and over time turns it into this one. Do you agree? At time 0, I have the initial Hamiltonian. At time 1, I deformed it into H prime. And hopefully I did it in some continuous way, such that, meaning that, smooth way, such that f of t is a smooth function. Okay? One way you can think of this is that, this Hamiltonian really is just some set of matrices H of k, do you agree? Where it's a matrix that depends on this k, do you agree? And so you can think of this as for each, so you can think of this as f of t as outputting some h of t of k, right? So it depends on the time and the momentum. And so you just want this matrix to depend continuously on t and k. And you want this matrix to always have a gap between the eigenvalues.
What do we mean by smooth exactly? Because we can't do. What does we're just saying continuous?
Smooth, differentiable. Come up with you can come up with some way to take derivatives of operators, right? Look, in what sense? You can always, once again, you can say that this operator is really, in our particular case, defined by some h of k, do you agree?
Okay, yeah.
And then I can, if I switch this, if I change around the parameters with time t, it will be just some matrix h t comma k.
Yes.
And okay, this is like n by n entries that depend on t and k, and that can be smooth. Okay, that's fine. Okay.
I have a question. So, when I look at the H prime, does
Yes.
it like related to perturbation theory?
No, not necessarily.
Okay.
Well, maybe you could talk about perturbation theory a little bit in this context, but no,
Okay.
it's not directly related. This is just, I'm saying there's one Hamiltonian and there's some other Hamiltonian.
Okay.
And I say that they're equivalent to each other if there exists a function like this.
Okay.
If there doesn't exist a function like that, they're not equivalent to each other. Okay. But then, what does this let me do? Okay, wait, sorry. And, okay. Now, I'm going to do like a kind of a tricky thing because I don't fully understand it myself yet. So I'll just trust me that you can do this. Is like you can define a similar equivalence relation, a similar equivalence relation on the finite Hamiltonians. Okay. For the finite Hamiltonians, this thing is even better. Do you agree? Because finite Hamiltonians, I have like finitely many sites, right? So I can really, if I wanted to, I can just write it down as like a really big matrix. Do you agree? And then there, this whole thing is even easier because you don't have the momentum. You just have one big matrix, and you hope that this big matrix depends smoothly on it. In the finite Hamiltonian, though, it's a little harder to talk about what it means by gap. Because remember, this gap was because I was able to plot this in momentum space in the periodic case. So I had an energy gap. But in the finite case, I don't have this momentum space stuff. I just have like discrete energy levels. And so exactly what it means by gap, I don't fully understand. I need to read the book again and think harder, but okay. Suppose you can define a similar equivalence relation. Do you agree? That preserves the gap in some sense, whatever that means. Okay, but in this case, it should make sense. So now, okay, so let this be the periodic Hamiltonians. Well, actually, I don't want, it's not, oh. So this is bad notation, sorry, because this is the set of linear operators, and I want self-adjoint things. So this is very bad notation. I don't know how to write down the set of finite Hamiltonians versus. Is there a notation for like set of self-adjoint operators?
I don't know. You just call it L star.
L star. Okay, sure. L star meaning like self-adjoint things.
Yeah.
So this is going to be the periodic Hamiltonians that have a gap. Okay, we'll define this to mean this,
Yeah.
not to be confused with what this usually means. And then we're going to define this twiddle of H to mean the finite Hamiltonians. That can be finite tight binding Hamiltonians. So these are periodic tight binding Hamiltonians. These are finite tight binding Hamiltonians. Okay. And now on this one, on the periodic ones, I have my equivalence relation that I defined here. Do you agree? So I can look at the set of equivalence classes, mod this equivalence relation. Do you agree? Yeah. Do you agree? And I can also look at the set of equivalence classes of this guy under its own equivalence relation. Do you agree? And so the big claim, and I'll do the claim and then we'll stop because we're over time. But this is the big claim and you should believe it and think about it. Claim. Okay. Is that pi induces an isomorphism between these equivalence classes. So I'll explain what this means in a second. What does it mean to induce an isomorphism? Okay. So the point is, so this has really multiple claims. The point is, I can define pi of an equivalence class of a finite Hamiltonian to be, I can take this equivalence class and send it to the equivalence class of pi of the finite Hamiltonian. Do you agree? So this was a finite Hamiltonian. Pi, what it did, it would take a finite Hamiltonian and turn it into a periodic one. Do you agree? So we had equivalence classes of finite Hamiltonians under this, homotopy. And I can take pi of that, and that would be, I'm defining it to be sending it to the equivalence class of the kind of projected periodic Hamiltonian. Okay? This is an equivalence class of finite Hamiltonians. This is an equivalence class of periodic Hamiltonians. Okay? And so the claim is that this map is one-to-one. Well, sorry. The first claim is that this map is well-defined and doesn't depend on the choice of representative. The second claim is that this map is one-to-one. So we need to check two things. One is this well-defined? And then two is check that this is one-to-one. Very good. But okay, so what did we manage to do? We, if we were to prove this claim, we had finite systems and we had periodic systems, okay? And we said, okay, let's clearly, there isn't a one-to-one way to connect finite systems and periodic systems. So okay, instead, let's look at Hamiltonians which are similar to each other in the sense that I can kind of smoothly turn one into the other without closing the gap. Without closing the gap. Do you agree? Because I want to keep the gap open to keep it an insulator. Do you agree? Okay. And then, very good. And then I said, okay, I can take my Hamiltonians and like split them up into groups according to, a group of, it's a group of all the Hamiltonians that are equivalent to each other under this equivalence relation, and the other group is all the Hamiltonians that are equivalent to each other, and so I can kind of split this up into groups. Do you agree? Let's split this up into groups. Do you agree? And then I can use like a similar equivalence relation, but up here for finite Hamiltonians, and split those up into these groups. Do you agree? And the claim is that these groups are going to be the same. While the Hamiltonians don't get mapped one-to-one, the equivalence classes are going to get mapped one-to-one via this procedure. Okay? And it turns out that these equivalence classes will be, will have some physical properties that maybe we can read off and think about. But this is kind of important because this is really one-to-one, meaning that from a periodic, by looking at a periodic system, I can infer surely something about the finite system, right? And that's maybe a little bit, maybe a bit surprising. You had some periodicity condition that actually tells you something interesting about the finite system. Okay. To me, it was surprising. Maybe it's not. Yes. The other thing is, so F is smooth, F is gapped, F preserves a gap. Oftentimes, you also demand that f of t and preserves some other condition. Like symmetry, or has specific form. Like, yes. So this is the big thing that usually, this is what I struggled with when understanding this whole thing, is that in topology, when you work with these homotopies, homotopy just usually means like there's a smooth way to interpolate between one thing and another thing. Like I can take this thing and stretch it into another thing. But in this physical context, what is often different is like the notion of homotopy. You don't want the homotopy just to deform this into another thing. You want it as you're deforming the homotopy, as you're deforming one Hamiltonian into another. I have to, preserve, like the Hamiltonian has to have some kind of properties, like some kind of additional properties. Like I can't just take it into any like self-adjoint matrix in between and end up with the Hamiltonian I want. Maybe I want, say, a certain matrix, because of some symmetry, I need certain matrix elements to say always be equal to each other, or something like this, right? Like have a really particular system. So as I try and deform this one into this other one, I want like these two matrix elements to always be equal, for example. Like that could happen. And then you'll realize that that kind of homotopy is not going to be quite the same as like some other kind of homotopy. Okay? Right? Because in principle, if I was to just look at the space of all matrices, right? Of course, say 0, 1, 1, 2 is homotopic to, I don't know, the identity. Like if I just wanted to, like forget about the gap, forget about whatever, I just wanted a smooth function that goes from here to here with time. Do you agree? That's very easy. I could just do like something linear. Like I could do this plus t times this. Or actually, no. 1 minus t plus t times this. Okay? And then I increase t from 0 to 1. This one will be 0, this one will be 1, and okay, I'll have, yeah. But if I specifically enforced that that suppose I want a homotopy that preserves, this being equal to this, well, okay, that preserves this being equal to this, yeah, that preserves this being equal to this, these two off-diagonal elements be equal, for whatever reason I wanted to do this, then I would never be equivalent to this because this has 0 and this is 1. So then if I demanded that my homotopy preserves these two to be equal at all times, do you agree? Then these would always be equal to 1 and I would never be able to interpolate to this one.
May I pick a bad example because it want the identity anyway?
What?
0 equals 0?
What do you mean 0 equals 0?
You want the
0, 1, 1, 1. This is 1, 0, 0, 1.
Yeah, you said you want off diagonal space, or whatever.
Yeah, so I'm saying I want these to be equal.
Yes.
So say I wanted homotopies, which like keep these elements to be equal. Do you agree? Then I can never deform this into this. Do you see why? Because if I try to deform this into this while keeping these two elements, actually no, yeah, you're right. I can't do that. You're right. Never mind. Sorry. Maybe I wanted them to be constantly equal to whatever they. Okay. Yeah. Sorry. This is a bad example. But the point is, I can. Sorry. Forget about this.
Yeah.
But the point is, like, I can add additional restrictions rather than just a smooth thing, and that would change which things are homotopic to each other. And these additional conditions often come from some kind of physics. Okay. Yeah, I'll stop here, I think.